temperature, if you recall from a couple of slides ago, is something that we can access in a colloid experiment. Okay? Of course, the EK transition, we're never going to get there, like I told you. Okay? But across the dynamical transition, what is expected to happen is that the heterogeneities that I showed you a couple of slides ago, those pink guys, are supposed to change shape from these sort of ramified objects to more compact objects. And that's one more thing that we can go and check in an experiment. Okay? And more importantly, what it tells you is that the surface tension, basically if you were to cool the system, the surface tension is going to jump to a finite value when the mosaics form, and the goal is to see if we can actually measure the mosaic surface tension. Okay? So, and of course, you need to be able to measure a growing mosaic size, a growing static correlation length. Okay?
What is the driving force for the shape change?
Oh, so the driving force of the shape change is in this. You're at a high enough temperature, you can sample many configurations, and a stringy object allows you to have many microstates, as opposed to when you cool the liquid, you don't give it enough temperature, so the more stable state is a compact object. So it's purely, so the surface tension and the configurational entropy are the two key parameters which decide such a thing from going on, and also they decide xi, which is my static correlation length, and so you need to measure the finite surface tension. So the theory says it should be there. Okay. 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 So how does one go about measuring the mosaic size? Like I told you, you have given an amorphous state. How does one go about doing that? And these people came up with a very clever way of doing it. Okay. And the idea is, let us say that this is indeed my mosaic state. What I'm going to do is, I'm going to freeze all particles outside of a cavity. All right? I'm going to freeze all particles outside of a cavity of radius r. And now, a mosaic is an object that reorganizes cooperatively. So if I pinned everybody at the boundary, there is no way the mosaic can reconfigure. Right? So if my radius of the cavity is much smaller than the mosaic size, and I look at the dynamics of the particle at the center, I am never going to be able to reconfigure. If my cavity is very large, then I can have multiple mosaics inside the cavity, which means that I should be able to reconfigure. Okay? So essentially the idea is to do this for each temperature, for each degree. Yeah, so you basically see if the particles have, so I'll tell you what we measure. Yeah. And the quantity that you're going to measure is what's called the configurational overlap. Okay, so what you're going to do is you're going to grid the system into small boxes, and you're going to measure this quantity. You see, it looks almost like a density correlation. Yeah.
What is causing this cooperativity?
Oh, what's causing the cooperativity? We don't know. We just know that it exists. But you can imagine that in a dense liquid, the only way you can move is if a bunch of guys around you move. Right? So you can imagine yourself in a crowd, and it exists. So the question is, the cooperativity that we see, is that even related to the slowing down, is something that's debated. Okay, but we know that it's universal. It happens across all glass formers. Okay. Yeah. So we're going to measure this quantity called the configurational overlap. Okay. And what you find is, so you freeze the cavity. You look at the particle dynamics in the center. Now, if the boundary is really influencing the dynamics of the single particle, it means that there is some static order, which is why the center particle is being influenced. Okay? There's some sort of static order, and if the cavity is much bigger, then this particle in the center is not going to be influenced by the cavity, by the particles that are pinned to form the cavity. Okay? So the idea is they did this for a whole bunch of experiments, so a whole bunch of different temperatures, and what they do find, you see, this is a joke, right? So xi grows by about about a factor of 2 across the glass transition temperature. Okay, if you showed this sort of a plot to people who do critical phenomena, they laugh at you. Okay, because this sort of a growth is you have a relaxation time that grows by 12 orders of magnitude, and you have a static length scale that grows by a factor of 2. Okay, so nobody buys this sort of a growth anyway. All right, but I'll tell you why it may be the case, why it might be useful to.
So what is xi?
Oh, so xi, okay, xi is the length scale at which is the radius of the cavity at which the particle at the center is influenced by the boundary. Beyond that, it is no influence.
That's what we call it as the mosaic size.
That is what is supposed to be called the mosaic size. And the idea is it's supposed to diverge, and that is the divergence that you get. Okay.
And Xi naught is the mosaic size at the.
Yeah, you just rescaled it by some. So what you do? No, Xi naught is something you can. It could either be a 2-point correlation length. So you just divide it out so that you can show it on a scale like this. So you can compare different glass formers. But this is a simulation, so this is essentially done, I think, for 2 different glass formers. So I really don't know what Xi naught was. Okay, so that's what they proposed. And later on, the same idea has been taken forward to many different sort of pin geometries. Okay, so this is, you can freeze particles at random. You can freeze particles inside a cavity, but in essentially all of these spin configurations, what you measure is nothing but the configurational overlap or the self overlap. And the difference between these two quantities is, in one case, you don't care if the same particle occupies the box. In the other case, you do, because you see, all I do is I divide the system into boxes. If a particle is occupying a box, I call it a 1, otherwise it's a 0. In this case, it has to be the same particle that occupies the box. Okay, and this is exactly the quantity that you measure in dynamic light scattering. Okay? It's the density correlation in a way, where the box size is your wave vector. Okay, the goal is, of course, how do you do this in an experiment? Okay, so this is our experimental system. Bidispersed particles. We're going to do 2 experiments. One in which we freeze a wall. One in which we have the free liquid. Just for that we can compare. We have a binary system so that it forms a glass. And the way we freeze the wall is the following. So this is the snapshot of what we see in a microscope. These are the particles that we're going to assume form a wall. Then we're going to basically calculate the Fourier transform of these quantities of the particles where we want to form the wall. We feed it into an optical tweezer, and the optical tweezer basically creates a whole bunch of different traps at once. Okay. I won't go over the details, I'll be happy to talk about it later, okay. So this is an image in which you see the rest of the liquid is relaxed because it's all a uniform gray background, except the wall has been frozen, okay. So we can form this wall in an experiment, right. And the idea was to see, the first thing is go ahead and measure the static length scale, okay. So I won't go over this again. So we measured the static length scale, okay, from measuring the configurational overlaps. We can do it for the same, we can do the same thing for the dynamic length scale, okay, you do the self overlaps, okay. But the interesting thing to note in the self overlap is that for one particular volume fraction, which is very close to what's called the mode coupling temperature, we saw these 2 slopes, okay. But don't worry about that yet. From all of these sort of, from this sort of data, you can basically use these relationships to pull out a dynamic length scale and a static length scale, okay. So the static length scale grows, and the dynamic length scale goes through a maximum, okay. So this is from our experimental data, in which and one more, the growth is about a factor of 4, but you see that right across this dynamical crossover temperature, where RFOT says the mosaic state should form, you actually see the dynamic length scale come down. And one of the problems in the glass physics community has been that dynamic length scales have always grown faster than static length scales. So people say that why are you even associating it with the thermodynamic transition? But the fact that it shows a non-monotonicity means there is some temperature window in which dynamic and static length scales grow the same way. Okay, it goes through a maximum and it comes down, okay, and we expect that if you were to cool it further down, these 2 would follow each other, okay. But and one more thing, it was seen in simulations earlier before us. But the thing that we did is that across the dynamic crossover, I told you that RFOT predicts a change in the shape of these mobile particles, right? So what we did is to basically look at all the mobile particles. So you can look at each colloid, ask how much it moved. You can cluster them in space. And what I'm showing you is basically the number of nearest neighbors for a fast particle. So I identify a fast particle. I identify if the neighbors of this particle are also fast, okay? Which tells you that I am in a dynamical heterogeneity. And if I have only 2 nearest neighbors which are fast, it means I'm mostly a stringy object. And if I have more than 2 nearest neighbors, I'm a more compact object. So I can look at the number of nearest neighbors for a fast particle. And what you see is that this guy at low temperatures is peaked at 2, but at much higher, at low volume fractions it's peaked at 2, but as you increase the volume fraction, it moves to a larger number.
So this is dependent on, because you have a binary state, right? Fast or slow. You have to calculate your quantization number, you either define it to be a fast.
No, so what I do is I've identified the fast particles in my liquid.
So this is like a threshold.
Yes, this is like a threshold, yes. And depending on the number of fast nearest neighbors, I quantify it as a stringy object or a compact object, okay?
Either your particles are fast or the particles are slow.
No, the particles are fast or slow is quantified by looking at whether they broke a cage or not, or whether how much of the particle size they moved really over some very small interval in time. Yeah?
These are not dependent upon what the threshold you choose.
So we have checked it for a whole bunch of thresholds. The results that I'm going to show hold.
So when you say fast moving,
Yeah.
are you talking about a specific kind of that they have to go in some direction, or they can be just shaking back and forth on the same?
Oh, that okay. So, I should have been a little more clearer. When I say fast motion, vibrations within a cage don't really contribute to relaxation. So you really need to hop out of a cage. So we're looking at displacements that are larger than the cage rattling size. And for every volume fraction, we really know how to pick up this number. So because we know how much rattle room there is available, and you can always set your threshold to be larger than that. Yeah, and then based on, and I don't want it to move too much also. All right, yeah.
Have in principle real space and time data.
Yes.
Okay. Is it okay to use continuity equations to look for from density to go into currents, or is the continuum picture of continuity equation doesn't make sense? You know, if I have the rho of RT, but looking at del T of rho of RT, if the continuum description is okay,
Yes.
I should be able to get grad of J or something like that.
Yes.
So now, of course, you have discrete things. So, but
Yes, I have discrete objects, so I'm not sure.
Yeah, so that's what I was asking. Is it okay to take a continuum description? Whether you can get velocities out, maps out of this. That's what I was asking.
So you can get current maps, but but we have not looked at that specific quantity here. I don't know what more is involved in calculating that. Okay, so essentially what we did is, so that is your non-monotonicity that we observed, and in our experiments we did observe that the objects, the CRR shapes or the dynamical heterogeneities did go from kind of stringy objects to more compact objects. Okay, and this is a prediction that's unique to RFOT. There are many theories of the glass transition, but only RFOT says they should happen. Beads are polystyrene, yes. Liquid is water. Yes.
What is the phi here?
Oh, phi is the area fraction because I'm in 2D.
Okay,
So it is like an inverse temperature.
okay.
Yeah.
So your area fraction means you are compacting.
No, I'm not okay, so yes. One way to do it is to look at the reduced pressure, but what we do is to just increase the number of particles per unit area by sedimenting them into cell. So we have various of the sample cells. We just leave the sample standing. Particles accumulate at the bottom because they're heavier than water. Then we let it lie down flat, and you start having systems which are at different area fractions. That plays the role of an inverse temperature.
So you change the solvent from
Yeah.
water to say benzene or some other solvent, non-porous solvent.
Okay.
How does this fix?
Oh, so the real role of the solvent here is to just give it thermal kicks. So we don't care if it's benzene or water, but if you throw polystyrene benzene, it will just open up.
Because polystyrene is non-porous.
Yeah, but what I'm saying is, what I'm looking at is the collection of particles, how they are behaving with the solvent playing the role of a thermal bath. You could take any other particle that is inert to the solvent that you're looking at, and everything that I'm saying should fall through.
Because the solvent is colloid deep interaction easily.
The solvent?
And the solvent of colloid polystyrene versus water interaction versus polystyrene versus say.
So these are screen Coulomb. So there is a surface charge. These are charged particles, but we throw in a little bit of salt so that we can get it really close to hard spheres. But they're not really hard spheres. You need a different system to do that, but it doesn't matter. But what I'm saying has been found, not the shape change, but everything else that I've said so far has been seen in a whole bunch of different colloids. Okay, all right. So we saw the shape change. And I'll skip this in the interest of time. And we also saw the shape change happen if you make particles that look like ellipsoids. So these are ellipsoidal particles that we made, and once again we see the shape change. And we also were able to show that everything that we saw, the non-monotonicity in the dynamic length scale, the growing static length scale, and the shape change were inconsistent with the theory called as the dynamical facilitation theory, which I told you earlier predicts a transition at t equal to 0. So in the limit in which you are accessible, you can still distinguish between these scenarios. Okay? Oh, so yes, the facilitation theory basically says that the only sort of relaxation that can happen are stringy relaxations, but we showed that that's not the case. Okay? Okay, and at the end of this study, we were pretty confident that, like the RFOT sort of a scenario, we didn't show you mosaics, I haven't shown you surface tension, kind of agrees. I have 5 minutes?
Yes, 10 minutes.
Oh, okay, 10 minutes, all right. Okay, and which is why I put in, our observations are consistent with RFOT when I pinned particles. Okay, now you see the other gang is not going to keep quiet. All the non-RFOT gang is not going to keep quiet. And what they basically said is, yes, you can go and do all your RFOT on pinned liquids, but that pinned liquid is not even the same as the liquid that you started off with. Okay? By pinning particles, you have ruined the liquid that you're interested in studying. And these are all the other guys, the DF guys, the geometric frustration fellows, all of those people came and said pinning is just the wrong way to go about doing this. All right? I won't go into the details, but I'll be happy to talk to you if you're interested. Okay? I pinned the particles by turning on optical tweezers, but it doesn't matter. In simulations, they just froze a particle. So they have the positions of all the particles, they pick a wall at random, a cavity at random, and just freeze it. But the trouble was optical tweezers.
So, yeah, but you are putting, so you want to put one particle or many particles?
I froze a wall in my experiments. But it doesn't matter. These papers cover the entire spectrum. Disordered walls, random pinning, cavity pinning. They just said